All right. Is the TV going to come on? Let's see. There we go. All right. Let's go get started. Welcome to Steel Design. I hope everybody was able to navigate the perpetual bank robbery alarm that goes out in the hallway every day. Every day.
We're going to have to move this bathroom. I just don't understand. It doesn't make sense.
See right there, don't L word logic. That's a curse word around here. Don't. It's a dangerous word to be used to thrown around. You're making sense. There's well. Yeah.
It's beef, but it means it works.
There's this famous physicist. There's this famous physicist who has this line. He says, "The universe is under no obligation to make sense to you." You know? Oh yeah, man, that's bringing it back. Mel Brooks. Mel Brooks. That's where it's at. All right. So welcome back. A couple things. I'll be the first person to admit I had let the YouTube playlist slide a little bit. The videos were uploading. I had forgotten to, or hadn't had the time to upload them or add them to the playlist. Everything's up to date now. I've got all the grades and all the materials up to date on Blackboard as well. If you haven't already done so, I've got 3 column handouts. If you haven't already done so, grab one apiece. We're not going to use these today or even get into them next time, but I wanted you to go ahead and have them for the days to come. Our second exam is going to be on bolts and welds, so it's actually going to be it's not going to be on a lot of material. A lot of the design procedures and a lot of the concepts with columns and beams tend to go quite well together. So columns and beams are going to be our final, and then bolts and welds, that's going to be our exam 2. Traditionally, exam 2 is one of the, or I'd say is the easiest exam in this class. So hope that's all right. We'll have that exam, like I said, we'll have our review the Monday before spring break. We'll have the exam the Wednesday before spring break, and then the Friday before spring break. Since we haven't had any snow days, we'll just call it. Is that okay? Well, in here it'll be the 20th, 22nd, and 24th. Those days we won't be here that week. Yeah, something like that. No, 3, right? Yeah, today. Yeah, 3 weeks. And we're only going to be on welds are only going to take like 2 lectures. They're not going to take a lot of time. That Friday, yeah. The Friday before spring break, yes. Assuming that the university, assuming we don't have like a blizzard in the next 2 weeks. So, yes. If we don't have a blizzard in the next 2 weeks. That's what those days are for. So, yes.
You have a concrete exam 3?
I do. What's that? I do. I got them. I will at 10 o'clock. I don't get the reference at all. You do, though. I don't get the reference.
Okay, there's a video of this kid. His parents gave him an avocado as a Christmas present. And he opens it up and goes, "An avocado! Thanks!" It's like when you get a gift you really don't want. Like the example.
Like giving your kid a crappy Christmas present, most of their bits, and he's like, "Oh, an avocado."
Well, I know there's the one he does. Isn't there the one he does where he goes to, he tells the parents to go to their kids and say all the Halloween candy's gone, or something like that, and they freak out. All right, real quick, bolted connections. We do still have a homework assignment that is due on Wednesday, so I figure I should take some time and entertain any questions in regards to that assignment. I know I'm not extending the due date on it. I knew some of you were like, so about that due date on Wednesday.
Yeah, like Daytona 500 was yesterday.
The Oscars were yesterday.
I mean,
Well, that was yesterday. This is today, and it's not due till Wednesday, so.
just a lot of if you're a Kurt Busch fan, it can be a long year.
Any questions at all whatsoever about the bolted connections homework?
For the second one, like how much, like what all details do you want for our layout?
Okay, let me pull up the actual homework so we can all speak intelligently. So I do want the answer. I'm just kidding. Yeah. In all seriousness, okay, so here's the connection that you're designing. So what I need is so there's going to be two lines of bolts, so you need to know the spacing this way and this way, and you can get that from table 17A. Is that what I said, 17A? And then I need to know the spacing of bolts in this direction. So you'll need distance requirements for that first row and then spacing accordingly. So if you're going to have two lines of bolts, don't pick 7 bolts. Pick an even number. So there's that. You do need to do bolt bearing checks on this connection as well. But be clear, these are both the same grade of steel. So if you have the angles, which have a total thickness of 2 inches, and then the center plate, which only has a thickness of 3/4, which do you need to check, the angles or the plates, considering they're the same grade of steel? The 3/4 inch plate. You don't even need to worry about the angles. Does that make sense? Did that answer your? But yeah, I need the answer is a drawing or a schematic of the connection. But let's be clear, you have to go through and check bolt bearing, okay? Although for this connection, you only have to check the 3/4 inch plate.
You can check bolt bearing, and like your bolt bearing is much more than your load.
That's fine. That's fine because think about it like this. All right. So the question was, if you go back and you check your bolt bearing capacity and you find that your load is 200 kips, but the bolt bearing capacity is 500 kips. That's fine, and that's not that uncommon. What that means is that bolt bearing does not govern that design. In other words, if I take that connection and I start yanking on it, what's going to happen first, if all I care about is bolt shear and bolt bearing, what's going to happen first is that the bolts are going to shear in half. You see what I mean? It's very possible that you could do a check and find that bolt bearings got, what was it, bolt loads of capacity? Is that what it is? So, no, but in all seriousness, you could find that, 200 kips in load and 500 kips in capacity. There's nothing wrong with that. Okay? It just means that that particular check doesn't govern. But let me also be clear, there's no alwayses and nevers associated with that. Like, that won't always be the case. I mean, if you've got really large bolts and really low spacing, you can find that bolt bearing governs. So.
Bolt bearing, is that high compared to the load? Needs to take off bolts or
No, that's a good question. The answer is no, because let's be clear. Let's say your load's 200 kips. Let's just keep it simple. Let's say your factored load's 200 kips. Now, if your bolt bearing capacity is like 500, that's great. But if your bolt shear is 220, well, you can't start taking off bolts, because if you start taking off bolts, you'll violate bolt shear. You see what I mean? So it's almost like you could have, massive amounts of bolt bearing capacity. In the end, it doesn't really matter, because your bolt shear is what governs.
I feel kind of dumb right now, but what's the difference between bolt bearing and bolt shear?
Okay, bolt shear is the bolt snapping in half. Bolt bearing is the plate failing. Like, hold on. This is what I mean by bolt bearing. Either the plate wanting to tear out or the bolt hole wanting to stretch and ovalize. Okay? When we check bolt shear and bolt bearing, we're checking one of two things. Bolt shear is the bolt, shearing in half, and bolt bearing is this happening. Now, if you're getting a bolt bearing capacity of 500 kips, what you're saying is it takes 500 kips for this to happen. And I'm saying, that's fine, but if bolt shear, if its capacity in bolt shear is 200 kips, that's what governs. I'm saying the bolts will snap in half before this happens. Does that make sense? Anything else? Remember, I did have one quick question on problem 1. Here, let me skip down to here. Here we go. Okay. On problem 1, and I do apologize that problem 1 is a little bit of, shall I say, busy work, but it is what it is in the world of connections. I think it's actually kind of important to go through this exercise to make sure you understand what's going on. First off, each, like if I count up the entire number of bolts in this entire connection, okay, I'm talking top and bottom. I've got what? 8, 16, and that's on the top. So I've got 32 bolts in the entire connection, right? But when I do my analysis, I don't take the capacity of a single bolt and multiply by 32. I take the capacity of a single bolt and I multiply by 16, because it's all about recognizing that half of the bolts are transmitting the load to the left and half of the bolts are transmitting the load to the right. And the easiest way to explain that is samurai sword or lightsaber right through the center, okay? Because if I look at this, I've got an I-beam or a W section going like this, and then I've got 2 plates up top transmitting load like this. Okay? So in this instance, if I'm cutting a section and either looking to the left or looking to the right, I'm not seeing 32 bolts, I'm only seeing 16, 8 up top and 8 below. Right, does that make sense? As for bolt bearing, when you check bolt bearing, you really only need 4 things. You need a spacing, you need an edge distance, you need a thickness, and you need material properties, specifically F sub U, right? Now I propose that for, let's just keep this straightforward, for the W section, the blue shape, okay? The W section is going to have a spacing, an edge distance, the thickness, in this case we're talking about the thickness of a flange, or if you want to say 2 times the thickness of a flange, like take your thickness and multiply it by 2 and then just calculate, or you can calculate the capacity of a single flange and multiply that by 2. As long as you're counting for both flanges, you can do it however you want. But you're going to have a spacing, an edge distance, a thickness, and an F sub U. I propose that the W section has a set of quantities related to that. You know, the spacing, I'll go ahead and give you the spacing. So the bolt spacing is going to be, what, 3 inches for the wide flange? And based on what you see here, you can determine the edge distance and the thickness for everything else. I'm going to leave you all to determine that, okay? Now that's for the wide flange. The cover plates are going to have their own separate set of quantities. Maybe it's the same spacing, but they're probably going to have different edge distances, different thicknesses, and different F sub U's. So you take that set of quantities, compute a phi RN. Take the other set of quantities, compute a phi RN. That makes sense? Minimum one of those 2 in bolt shear is what's going to go. Sound good? Yes? Not necessarily, okay? Think about it like this, all right? I will help you out with that for a little bit. So if I look at this cover plate, okay, the cover plate. So remember, I'm cutting a section right through here, right? Make sense? Like I'm cutting it right through that center part. So I propose that's your cover plate. Bam, 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 bam. Oh, I did not space that very well. Bam, 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 bam. Sound good? Now I'm taking this plate and I'm yanking on it, right? Now let me ask you a question. Which ones are the edge bolts? The ones over here or the ones on the right? The ones on the left or ones on the right? The right, okay, for the cover plate. Now for the wide flange, which ones are the edge bolts? The ones on the right or the ones on the left? The left, okay? Now you look at this, you can see maybe they're the same dimension, maybe they're not, okay? Make sense? In other words, what if this was 2 inches and that was 1 inch or something? Sound good? The big difference, though, is that even if the dimensions are the same for the spacing and the edge distance, they're going to have different F sub U's and they're going to have different thicknesses. Okay? Sound good? Any questions? Does this help out a little bit? Okay. Remember, Wednesday. Due on Wednesday. Sound good? All right. Then let's get into a little bit of discussion about welds. Because welding, I'll be honest, I think welding, by and large, is easier than bolts. I think the details are ultimately a little simpler. And when you get right down to it, the math, the concept is just as easy, but the details are fewer and far between. So let me just sort of start back here. I'm going to skip through some of this intro stuff pretty quickly, but we'll get into the math and maybe even get into a little bit of an example today. Okay, so last time I know we were at a little bit of a rush, and I know that you all were, many of you were concerned about the concrete exam that was coming up, so I'll go through some of this in rapid detail. So I just wanted to at least briefly mention AWS, the American Welding Society. A lot of what we do for welds basically gets adopted straight from them, so it would be remiss of me not to at least mention AWS. Specifically, their D1.1 structural welding steel. It's one of the most consulted codes on earth. So a lot of what we do gets derived directly from D1.1. We talked last time a little bit about welding procedures. You know, these are the technical names, you know, shielded metal arc welding, gas metal arc welding, and what have you. But you probably know of them in different terms. Like, for instance, you might not have heard of shielded metal arc welding, but you've probably heard of stick welding, right? Probably heard of stick welding. You've probably heard of the process. You've probably also heard of MIG welding, right? The difference between stick welding and MIG welding. By and large, most of the structural welds that we do use stick welding, especially the ones that have a fairly high capacity. But honestly, I'll say this. For the purpose of what we're interested in the realm of design, I mean, in ways we kind of put a little bit of a blinder on this stuff in terms of design. You know, all we care about is, okay, the weld is 6 inches long, it's deposited with this electrode, and it's this thick. That's all we care about, okay? We don't really, I mean, yeah, we need to know how the weld is deposited, whether or not it's whether or not it is a stick weld or a MIG weld. I mean, it's nice to know, but it really doesn't affect what we do. So, all right. There are a couple welding procedures that I do want to go over that you might not have heard of. Now, we talked about flux cord arc welding, which is basically just a MIG welder that uses that electrode that has the flux on it. You know, you can probably tell when you've seen it used before that it has that sort of white sooty deposit that comes on afterwards. That's just the, I don't want to say it's the cheap way of getting around it, but it's the way of getting around welding without the gas. You know, you get the gaseous shield from the flux that's on the wire. Now, one welding procedure that you probably haven't seen, but you will if you are working with a large-scale fabricator, is submerged arc welding. One of the things you'll find about submerged arc welding is all the action sort of happens under this granular flux that's deposited in front of the welder. So there's not as much of an issue with the light. Like, if you've ever been around welding, I mean, what do they tell you? Don't look at the light, right? Because it's a very bright light and it can cause damage to your eyes. But that's not really an issue here. The reason why is because of this. So there's a granular flux that's deposited in front of the welding, or the stream of weld, and all of the welding sort of happens submerged under this. This is used for really, really long continuous welds. So, for instance, if you've got a a flange that's being welded to a web for a really, really large plate girder. This is the way that that large-scale fabricators like to do it, because you get a more uniformly deposited weld, and it's a little bit easier. Now, you have to spend a little bit of money to actually buy the equipment for this, which is why I say large-scale fabricator, but it's starting to gain more and more popularity. Everybody kind of get the idea with this? Okay. Now I want to talk about the different types of welds that we actually place. If you've ever welded anything, you've probably heard of a tack weld before, am I right? Now, a tack weld is not a structural weld in any way, shape, or form. A tack weld is really just a short little hit of the electrode to get the piece in place. So the idea is you're getting ready to weld some frame up. You know, if you're out in the auto body shop and you're welding up a frame for a new car, you got your tube steel and you got it all bent up and ready to be put together. The first thing that you will do is you'll get everything lined up and get it, you know, exactly where you want it, and then you'll place a small little tack weld. Okay, and the tack weld is really just to hold it in place. Okay, usually what's done is you'll get the piece in place, put a little tack weld, take everything off and go back and measure it again. If everything's where you want it to be, then you can go through and start placing the rest of your weld. If not, well then get a grinder and grind it off. No big deal. But if you place your full fillet weld and then you find it's 1/8 of an inch off, now you're going to be sitting there grinding all day. Okay? So tack weld is the first weld that you place, but it's not a structural concern. It's just more of a fabrication issue, just making sure that the piece is in place. Now, by and large, the most common weld, period, any way, shape, or form that is placed by a structural welder is a fillet weld. Okay, fillet, no fillet. It's a fillet weld. It's not fillet. It's
Is it a T-bone?
it's not a mignon weld. It's a fillet weld. All right. By and large, this is the most common weld that's placed, period. I have here 85%. I'd say it's probably more like 90% of all welds that are placed anywhere in any welding capacity are fillet welds. You have plate A, you have plate B, lapped onto one another, and a bead of weld placed in between. It is the most common weld that you will see anywhere. Okay, and is what we are going to be designing in here are fillet welds. Okay. They can be continuous, you know, just one long bead of weld. They can also be placed in discrete lengths. They're called stitch welds, like you have a little bit of fillet weld, then a little bit more, then a little bit more. Kind of looks like a stitch. But in the end, it's still the same idea, a bead of weld lapped between two plates. If 85% of welds are fillet welds, I'd say another 10 to 14% are groove welds. And a groove weld is really meant to splice two plates together. And it's really pretty straightforward. You have plate A, you have plate B. You grind usually what you'll do is you'll grind a groove in between them, usually like a V-shaped groove, butt them up against one another, fill it with weld metal, and that's essentially it. One of the things about the design of a groove weld is, in terms of structural design, there really isn't any. The details and the amount of weld is placed such that the strength is governed by the strength of the base metal, not the weld metal. I mean, think about it like this. If we designed every single tension member such that gross section yielding governed, and we would and net section fracture would always have a higher capacity, then we really wouldn't ever need to check net section fracture capacity if we always knew it was higher. See what I mean? It's kind of the same idea with this. The weld metal capacity is always going to be higher, so we really don't need to check it. Now, there's really two common types of groove welds. We either have CJP or PJP, standing for either complete joint penetration or partial joint penetration. But in the end, the process is still the same idea. Sound good? There's a couple others that I think I should mention. Plug welds or slot welds, they're pretty rare. But the idea is you have a plate on top of one another, and you'll have like a, let's say, a hole drilled, and you'll fill that hole with weld metal. And it can be used to like transmit shear and lap joints and things like that. But in the end, they're pretty rare. Fillet welds and groove welds are going to get you through 98 to 99% of the welds that we do in structural steel design. Sound good? I've been mentioning lapped. What do I mean by lapped? I've got here a series of images that kind of just give you an idea of what I mean by welded joints. So, for instance, a lap joint would be a plate on top of another plate, and the weld would be placed, you know, somewhere in here, maybe somewhere in here. A T-joint, maybe you've got a web being joined to a flange, and you're wanting to weld here and here and what have you. You can also have a butt joint. This would be more appropriate for, like, or more common for things like a groove weld, CJP, PJP, where you're taking two plates, butting them up against one another, and then welding them together. Okay. Let's see. One thing that, and I think this is more of a fabrication issue, but I think this is, there's definitely some respect that needs to be given to a qualified and skilled welder, because one of the things that really matters is weld position. Okay. For instance, I would argue that it's pretty easy, comparatively, to place a flat weld as opposed to an overhead weld. Okay. Because, you know, most welders would love to place flat welds because they're taking the part and they're oriented the way that, you know, you want it to be placed. You sort of just want to be filling it in with weld metal. Whereas if you've got a vertical weld or an overhead weld, I mean, you're literally having to do that and maintaining a consistent speed so that that weld metal literally doesn't drip out. You know, that gets kind of tough. And I just think it's worth saying that you know, a good welder is worth every penny, and the industry feels that way also. Welders, depending upon their certifications and what they're welding, can make a fairly decent salary because it is not easy. It takes a lot of skill. All right. Sound good? All right. Okay. I am not going to get into weld details and specifically weld symbols. If you look at a particular drawing and you look at the like if it's a fabrication drawing and it's calling out all different types of welds, I mean, it can look pretty complicated with all of the different symbols. For instance, if you have a symbol pointing to a given weld and it has a flag on it like this, that indicates a field weld. That's a weld that's done in the field as opposed to being done in the fabrication shop. For instance, if you have a weld with a square symbol, that's a plug weld or a slot weld, as opposed to if it's got a triangle, it's a fillet weld. I'm not going to be interested in you memorizing every single weld symbol that's out there. What I am interested in is that you understand what is on this slide. So what I have here are two different weld symbols, and as long as you understand what's going on here, I'm happy. So for instance, if I have here 1/4, I have 6, and I've got this triangle. Let's take what each of those mean one at a time. So let's start off with the 1/4. The 1/4 is the size of the weld. So, you know, the more passes of the electrode, the longer the welder is placing that joint, the larger the weld size is going to be, right? So this is a 1/4 inch weld. Now the 6 is how long it is. So in and out of the screen, this weld is 6 inches long. Okay? Make sense? The triangle indicates that we are placing a fillet weld, you know, plate on top of another plate, bead of weld placed in between. The triangle on this side indicates that the weld is going to be placed where the arrow is pointing. So the triangle right here means the weld goes here. If I've got two triangles, that's on this side and the other side. Okay? And the 8 corresponds to 8 inches long. That's it. If you understand that, that's all I care about. All right? The most common weld nomenclature that's used, period. So, yes?
What if you only have one triangle on the top? Does that mean
that
opposite side?
The opposite side, yeah. But that's not really used very much just because they put it over here. Yeah. But you're right. You are right. Sound good? This isn't so bad, right? Pretty simple stuff. And like I said, this is the most common weld detail you're going to see. Like what my interest is that if you're working on a building project or a bridge project and you see a bunch of arrows with a bunch of triangles, you know that they're talking about welds. That's really what I'm interested in. Okay. Okay, now let's start talking about the math, okay? And I think you're going to find this is pretty simple, all right? So I have here a detailed, sort of a more detailed analytical drawing of a weld. So you notice I've got a lap joint, and I've got plate A on top of plate B, and I've got a bead of weld placed in between. Now, one of the things you'll notice about this detail and about this drawing is we're automatically assuming that the weld is triangular. Everybody see that? That we've got a sort of a 45, 45, 90 triangle? Okay. Now I'm going to skip ahead a little bit to show you something. More off, what's that? No, I'm not going to show the video again, but it's on the playlist. But that was a good one, wasn't it? That was, I told you it was well worth it, see? It was a good one. There's another joke that I'm going to steal. I stole that one too. Let me. I'm coming up with more. I said I'm stealing them. Did you not follow along? I wanted to be clear on something with the detail associated with the weld. We're assuming that the weld is essentially a 45, 45, 90 triangle, but in actuality, the weld is really placed a little bit over that. You see what I mean? It sort of bubbles over. So I just wanted you to be clear that the 45, 45, 90 is really a conservative estimate of what's going on in terms of the geometry. Sound good? Everybody good on that? All right. Now, what I propose is that if we're looking at the capacity of the fillet weld, I propose that when we make an assumption in terms of capacity, we assume that all of the action is happening in this shaded area right here that goes from the root of the weld to the face of the weld. So what I'm talking about is this shaded plane right here. Everybody see that? Okay. Now I propose we have a name for that region that goes from the root of the weld to the face of the weld, and we call that the throat of the weld. So if you ever hear me say effective throat, I'm saying from the root to the face. I propose that when we compute the capacity of the fillet weld, we're talking about the throat. Okay. Now keep that in mind because that's going to become important later. But I want to make a point right now in regards to weld orientation. So if I have a joint and I'm applying a load to it, I want to talk a little bit about orientation. Okay, now I propose that this right here is what we term a longitudinal weld. Longitudinal weld, bless you. Bless you. I was waiting for it, I was like, it's going to happen again. All right. Bless you. Now, you know, you're pushing it there. I'm kidding. A longitudinal weld is a weld that is loaded such that it's parallel to the direction of the weld. Whereas a transverse weld right here would be perpendicular, or the load is perpendicular to the direction of the weld. Sound good? So I'd say an incline weld is somewhere in between. Now, watch it. If I take this weld, I go down to the lab and I yank on it until it fails. I do the same thing here and the same thing here, and I start plotting it. I'm going to get curves that look something like this. So this long, pronounced curve right here, that's a longitudinal weld. Okay. Now, as the angle changes and gets higher and higher and higher up until a transverse weld, this right here is a transverse weld. Okay. Now, I see a couple things associated with these curves. Okay. As the angle gets larger and larger and larger, I see two things happen. Number one is I see the capacity going up and up and up. Make sense? So if I didn't want to do all the trig and the math associated with accounting for the weld orientation, what would be the most conservative estimate? To assume they're all longitudinal or assume they're all transverse? They're all longitudinal, right? It's going to be the most conservative estimate because I get the lower capacity. But that's one thing I noticed. But another thing I noticed is that the more and more transverse my weld gets, the less and less ductility I get. Okay? Ductility is a really important parameter in the world of structural design. I think we're finding that out in other classes like concrete. I mean, in concrete, when we have a tension-controlled versus a compression-controlled beam, remember in that course, tension-controlled beams give you a lot of warning for failure, but compression-controlled beams, when they go quick. Remember that? Well, it's kind of the same idea here. Longitudinal welds give you a lot of warning before they fail, but when transverse welds go, they go quick. So if I ever am working on some project and you were the designer and I see you've got a connection and you've got nothing but transverse welds on there, I'm going to say, stick your hand out. You're going, okay, I'm going to go, no, don't do that. Okay? Don't do that. All right? I have no problem with you all using transverse welds, but they better be in combination with longitudinal welds. If you have only transverse welds, that's bad. And if you still don't believe me, there's a video about a certain handrail at a McDonald's restaurant in Oklahoma that I think convinced you last time. Okay? No transverse welds by themselves. All right? Sound good? All right. Now let's go back to that throat. All right? Now I propose that if this is idealized as a 45, 45, 90 triangle, I use that word a lot, don't I? Propose. If this is a 45, 45, 90, let's look at this from a trig standpoint. I can calculate the distance of that throat as 1 over square root of 2 times the weld size. That's just sine of 45 degrees, right? Or cosine of 45 degrees. It doesn't matter. All right? Sound good? Okay. So when we look at our calcs, I'm going to idealize that as 0.707. So this distance is 0.707 times the leg size. So far, so good? All right. Now, keep that in the back of your head. Now, I'm not going to say it. I'm just going to go for the capacity. Go to the spec, and the spec says that the weld capacity, or the capacity of a given weld joint, is some nominal stress times some area. It's funny how that equation's showing up quite a bit for these types of connections. You know, some limiting stress times some area. Okay. Now, notice some of you are opening the spec. We might as well go ahead and do that now. I'm on 16.1-113. So that means everybody who brought their manuals should be able to turn to that.
Together.
All right. Well, you can look at his, so. All right. Okay, now, got to bring your manual to steel design.
You announced that Friday.
I did, didn't I? All right. Let's get on to it. All right, so the capacity is listed as some nominal limiting stress times some area. Now, when we look at weld capacity, it's going to be a lot like what we did with bolt capacity. Remember, with bolts, we either had the capacity of the bolt or the capacity of the plate. We called the capacity of the bolt shear capacity, and we called the capacity of the plate bolt bearing. Well, it's the same idea here. It's either going to be the capacity of the weld or the capacity of the plate, or weld metal or base metal. Okay? So we're going to take each of those one at a time. Okay? Now, let's look at the weld metal. All right? Now, if you look at the weld metal, it says the values of the phi, the nominal weld capacity, and all of that are listed in table J2.5. So let's turn to J2.5. You can't miss it because it's a really big table that extends over a couple pages. It's on 16.1-114 to 115. Now I'm on the one that's on the right side, right? Over here, okay? Now if you look, you can see each of the listings in the table are split up by various categories. And I'm on fillet welds, including fillets and holes and slots and skewed T-joints. So this is obviously what I'm interested in, okay? Now if I'm looking at weld metal, okay, what do I see? Well, I see that the phi value is what? 0.75? Everybody see that? What is the nominal stress? Well, it's 0.6 times FEXX. Now, we'll talk about the FEXX here in a second. What about that 0.6? I mean, if I've got a weld and I'm loaded like this and I'm yanking on it, it's funny how that weld's probably experiencing some type of shear. Remember how if you've got a shear, there's a 0.6 associated with it because of von Mises. Like, oh, now we remember it. We don't have exams, we have celebrations. Now, okay, so that is the nominal capacity, but let's look at the area. See where it says area, it says CJ2.2A? Let's turn back a little bit. Let's go to J2.28, so 16.1-110. Well, if you had your manual,
I think that's the miles on it.
it does. I don't know. That is true. Maybe steel manuals don't, I guess. All right. Okay, so let's be clear. So we have a phi value, we have a nominal capacity, and we have an area. Okay? Now the area, J2.2A, what does it say? The effective area of a fillet weld shall be the effective length multiplied by the effective throat. So literally, how long the weld is times that throat distance. Okay? So we have a phi, we have a nominal stress, we have an area, there's the capacity of a weld right there. It's that simple. Now, the only thing that we haven't really discussed in significant detail are the electrodes. When you go to a place like Airgas or somewhere that sells weld equipment, you look at, let me answer this real quick now. When you look at trying to purchase different weld electrodes, they're listed in certain categories like E60 electrodes, E70 electrodes. E70 is very common, E80, E90. The FEXX is literally that number. So an E70 electrode, its electrode strength is 70 KSI. It's that simple. So that's just a lookup. That's just a value based on the classification of that electrode. Bless you. Yeah, that you have to know that. But I mean, go call Airgas, and when you buy an electrode, that's what you're buying. Sound good? Yes. Well, we're checking the capacity of both. So, and what I'm saying is that we're going to have a capacity of the weld and a capacity of the base metal, and the smaller one's going to govern the capacity of the connection. That's what I'm saying. You'd like that to be the case, but it's not always the case. But let me also further answer that by saying, for groove welds, that's more than likely the case. I'd say for fillet welds, that's actually not the case. I'd say your weld metal is going to have a lower capacity than your base metal, and we'll see that when we go through the math. All right? Sound good? Okay. Now let's look at the base metal. Now, if you go back to that same table, go to the base metal, and the base metal is governed by J4. All right, let's turn to section J4. So if you turn to section J4, J4 is split into a number of sections. So first off, we have J4.1, J4.2, J4.3, J4.4, J4.5. So I'm sort of exposing you to the anatomy of the spec. And you should, so you're going to be turning forward quite a bit. This is actually past where all the bolts are. We're going to be in like the 129 range, 16.1-129, like in that range. Now, if you look, the section is split into the following. So first off, section J4.1, the strength of elements in tension. What we would be talking about is something that's like this. We're talking about that transverse weld. If I look at that weld in the middle, I propose that that base metal, the adjacent to that weld, is in tension, okay? Which I think that's a bad idea anyway, okay? So J4.1, that's not the section that we're after. Now, if you skip ahead a little bit, J4.3, that's block shear. That should be familiar, right? All right. J4.4 and .5 are for elements that are experiencing compression or bending. In other words, if I'm taking that element and literally bending it or pushing on it. Compression and flexure, they need a little bit of discussion before we start addressing that, because things in compression and things in bending like to do things that, or like to do something that tension members don't. Things in compression or things undergoing bending like to buckle, okay? And buckling is its own unique snowflake, and we'll be spending a fair amount of time trying to assess that. For now, we'll just sort of move past that, because buckling that we do in here versus buckling that we did in Engineering 216, not even the same thing. Not even the same thing. So, yeah, it's a little bit more of a loaded question than that. Okay. All right. So if we go to section J42, and I'm on 16.1-129, we've got that the capacity, since we're talking about elements in shear, is 0.6 FYAG or 0.6 FUANV, okay? And notice the 0.6. Von Mises, right? It's popping up again because we're talking about elements in shear. So that's popping up. Now, when we compute gross area and net area in shear, it's the same concept. The length of the joint times the thickness, okay? Now, let's also think, when we computed net area, how did we do that? We said it was the gross area minus whatever area that we lost due to the presence of bolts, right? Well, there are no bolts. So gross area is going to equal the net area. So it's going to make our lives a little easier. For shear yielding, the phi value is 0.1, and for shear fracture, the phi value is 0.75. Yes? What? But we're handling that differently. We're looking at the capacity of the weld and the capacity of just the base metal. So we're treating them as sort of two separate animals. That makes sense? You're saying that the weld actually got like added to the plate. Is one with I see what you're saying, and I'm just saying from the spec standpoint, and just from mechanics, the weld, the component of the weld is going to behave a little differently than the base metal, so we're handling them differently. Does that sound reasonable? I like that is one with the base metal. I like that. Now, let me see. So there's two other things that I think are worth mentioning, and then we'll sort of stop for today. And that is, just like with bolts, remember bolts had minimum and maximum spacing and minimum maximum edge distance requirements? Well, there are minimum and maximum weld sizes and weld limitations as well. Now, for very different reasons, let me assure you. Okay, so for instance, the minimum size of a fillet weld. Well, think about this. Why would a weld have a minimum size limit? Okay, let me paint a scenario. Now, it's going to be a little bit of a ridiculous one, but bear with me. Imagine you had two 8-inch thick plates, really thick plates, and you wanted to place a bead of weld that's a 1/16 of an inch. Well, it's not a matter of holding. Let me ask you this. Have you ever heard the term heat sink? It's just going to suck in all that energy. You have to have a substantial enough of a weld so that it can actually be placed, okay? So if you've got let's say a 1/2 inch thick plate, your weld has to be at least 1/4 of an inch for the plate to actually receive that weld because it's going to become a massive heat sink. All right? Does that make sense? So you have to actually have something there for you to actually get a joint. So if the weld's too small, you're going to have a rapid cooling, and rapid cooling is not going to go very well for the weld. All right, that's for minimum size. Maximum weld size is either the thickness or the thickness minus a 1/16 of an inch. And the reason for the maximum weld size limit is, well, if the weld gets too big, you're going to start to melt the plate. Right? So for most connections, the maximum size on the weld is the thickness of that plate minus a 1/16 of an inch. So this is just to actually maintain the fact that there's a clear edge to that plate. Now for really, really thin plates, like 1/4 of an inch, we say, what the heck, go ahead and melt it, it doesn't matter. So, but that's for really thin plates, yes.
An example for like, I forget what type weld you call it, a place like this.
A lap.
Weld with like a T or something. Would it be different?
No, it's actually not. And that's a good point. You could theoretically just start welding like crazy. But you know, for this concern, let me also state though that if you had a T joint, right? You had a T joint and a T joint, and they were 1/8 inch thick plates, like really, really thin plates, you probably would have a hard time placing a weld that's like 3 inches long because you just melt right through the plate. You know what I mean? So I'd argue that these weld limits are going to be pretty reasonable for those types of situations as well, because you start placing this crazy weld, you'll just burn right through the plate. So that answer your question. That's a good point, though. The limits are primarily intended to maintain the geometry of that edge, but I would argue that they're appropriate in those situations also. Sound good? All right. I'm going to stop now because what I want to do is afterwards go into some analysis examples. Let me say this though, after this discussion on minimum and maximum weld sizes, I have a very nice little set of summary slides. You know, here's the capacity of the weld metal, base metal and shear yielding, base metal and shear fracture, weld limits, and we have some nice examples. So that's all I've got for this. Next time we'll actually start employing these to do some welded connection analysis and some welded connection design. And I think you're going to find this is pretty easy. It's really not that difficult. All right, that's all I got. I will see you all, most of you, in a few minutes.